Hello and welcome to this video, the second lesson in the Thermochemistry unit for Chemistry 30. In this lesson, we are going to define a term that commonly gets used as a synonym to energy in Chemistry 30, which is called enthalpy. We'll talk about enthalpy and some examples of enthalpy, as well as looking at different ways of communicating enthalpy when you have a chemical change. So we can have a chemical change whether it's physical, chemical, or nuclear. Enthalpy measures essentially all forms of kinetic and potential energy of a system. Now, kinetic energy, as we talked about in the last lesson, is a measure of temperature, and we can use a thermometer for that. But how do we measure potential energy? Potential energy, remember, is the energy stored in the bonds of a compound. But we can measure what's happening during a chemical change. So that's the key that we're going to be focusing on. Okay? When we have a chemical reaction, we are going to measure what we call the enthalpy change. Again, also just meaning the energy changed or the heat changed. Think of H as heat. Is heat lost or heat gained? Now, there is a formula that we're going to be using that teaches you how to calculate for delta H. There's actually a few formulas that teaches you how to calculate for delta H. We're not going to get into those today. We're just going to talk about what the variable would look like and what units it would have, as well as I mentioned how to communicate it. So enthalpy changes is usually in a formula written as delta H, and it is the overall energy change of a system. Usually, again, we usually use this delta H during a chemical change, a chemical reaction. So it's the overall energy change or heat lost or gained by the system. Okay? Now, depending on the formula you use, you may get an answer in joules or kilojoules. Kilojoules are usually the standard units that you're going to see. Now, with this, you're also sometimes going to see a little symbol, subscript, in front of the H. And that can tell you or illustrate for you what type of reaction is taking place. So R just means any reaction. But you might see, for example, an H with a little F in front of it. That means you have a formation reaction. And remember, formation reactions are when elements combine to make a compound. Another common one you'll see is C, standing for combustion. So generally speaking, a hydrocarbon combustion that we'll be focusing on in this unit a lot. This is the enthalpy change of that combustion reaction. Okay, so those are little letters that you'll see with the delta H and also an H, which we'll talk about in a minute. You may also see a not symbol. The not symbol means that this reaction is taking place at standard conditions, which are our SATP conditions, 100 kilopascals and 25 degrees Celsius. Now, the H. In our formula, we also are going to have an H. And H is a little different than delta H. Now, the H, remember delta means change, and the H still represents a change, but we need to use a different variable in the formula. So in our formula, we leave it as just an H to show that it's different than the delta H. And again, the delta H is calculating or representing the overall enthalpy change, whereas the H is known as molar enthalpy. Okay? So molar enthalpy is the enthalpy change per mole of a specific substance. You can find the molar enthalpy of, there could be 3 or 4 substances or more in your reaction. They might have the same or different molar enthalpies for each substance. We're going to learn again in the next lesson how to calculate that. Okay? But just keep in mind that molar enthalpy is measured in joules or kilojoules per mole, most commonly kilojoules per mole. And it again tells you the enthalpy change per mole of a substance, whereas delta H is the overall enthalpy change. Delta H is also measured usually in kilojoules. So if you pay attention to the units, delta H is kilojoules, H is kilojoules per mole. Okay, so really focus on those units. Units are huge in chemistry. So what kind of energy changes can we have in chemical reactions? So in a chemical reaction, as I mentioned, we're changing the potential energy when one substance is converted into other substances. The chemical bonds are sources of stored potential energy, and this is important, okay? Breaking bonds always requires energy. So when you have a molecule or a compound and you want to break it apart, you have to add energy to make that happen. That is an endothermic process. And when you form bonds, that always releases energy. That always gives off, or is an exothermic process, okay? Now the relative values of these two changes happening in a chemical reaction. Let's say I'm adding a certain amount of energy to break my reactant, and then only a little bit of energy is given off when I form my products. That change, the net change, think of it as vector addition. The net change, if more energy is required to break bonds than is given off when the products form, overall, the reaction is going to be endothermic. You're going to have to add energy to make the reaction take place. But let's say, on the other hand, you have to add a certain amount of energy to break the reactants, and then more is given off when the products form. Now, you're going to have a net change going down, so my breaking of the bonds was less than given off during my forming. The forming, again, always being exothermic. So overall, this reaction would be exothermic, okay? That information is going to come up on the next few slides here, but I just wanted to draw a representation of what that kind of looks like. So if the energy added to break the bonds is greater than the energy released when the new bonds are formed, as I mentioned, the overall reaction will be endothermic. An example of an endothermic reaction that you do want to be familiar with is photosynthesis. So photosynthesis is a reaction in which glucose is formed. It happens in plants where plants take in carbon dioxide and liquid water, and they're absorbing energy. So notice how energy is written here as a reactant. Whenever you have an endothermic reaction, it's absorbing or using or reacting with energy. So energy is on the reactant side of the equation. Your products, again, are glucose and oxygen. And of course, we always like to balance reactions, so that's why you have the 6's in front of everything except the glucose to make it all balance. Okay? So be familiar with the photosynthesis reaction, again, being an endothermic reaction. Whereas, before that, important to note that when you have, ignore that video for a sec, when you have a endothermic change and you are writing the delta H of that reaction, it is going to be denoted as a positive energy change. Okay? Remember in the last lesson I said we didn't really worry about a positive or negative in our answer, but with enthalpy we do. We do need to show whether it's an endo or exothermic process, and endothermic processes are always positive energy changes. So you'll have a positive in front of your value measuring, like I said, usually a quantity in the range of kilojoules. Now this little demonstration here shows an endothermic reaction taking place. So I think it kind of, there we go. So we have the mixing of two chemicals and it's cooling off the surrounding environment. As the reaction is gaining energy or absorbing energy from the surrounding environment, it's leaving the surrounding environment feeling cool. And if you have water on there, it can actually freeze the water and freeze the water to the beaker. So it's important to know that even though an endothermic reaction is gaining energy, the reaction itself, and for short, I write reaction as RXN. So even though the reaction is gaining energy, I guess I could put delta H, the surroundings are losing energy, okay? The surroundings, again, could be your hand, could be whatever air is surrounding it. And later on, we're going to actually use energy measuring devices that use water to show what's happening in a chemical change. Okay, so even though the reaction is gaining energy, the surroundings is losing energy. That means that the temperature change of the surrounding environment is going to decrease. It's going to go down. As the system gains that energy, it removes it from the surrounding environment. Okay, so if you were to feel this on your hand would feel cold. Now, when you have an exothermic reaction, the relative heights between breaking and forming bonds, less energy is needed to break the reactants than what is given off when the bonds form. A very common exothermic reaction that you also need to be familiar with is cellular respiration. Now, if you memorize photosynthesis, cellular respiration is just the exact reverse. The reactants become the products and vice versa. Now, this reaction, notice again how energy is now written on the product side of the reaction, which we'll talk more about today as well. The energy is being produced in an exothermic reaction. It is being formed. It is being released. These are all words, synonyms that we use to show that it's an exothermic reaction. Now, you might also notice that my glucose is a hydrocarbon, and it's reacting with oxygen to produce carbon dioxide and water. That is a hydrocarbon combustion, but notice how this is highlighted in blue. In photosynthesis, the water produced is liquid, not vapor. Most hydrocarbon combustions in an open system will produce water vapor, water in its gas phase. But here, in cellular respiration, being in our body at 37 degrees Celsius, it's going to be in liquid phase. That's going to become really important later on when we start doing some calculations to find out the energy values here, whether you have liquid water or water vapor. So make sure you're very careful with your states. Okay? So cellular respiration is exothermic, as are, and we're going to mention hydrocarbon combustions. But again, a hydrocarbon combustion is producing water vapor. Okay? Still exothermic. Energy is still a product. Energy is still being produced. Remember again, a hydrocarbon combustion can be any hydrocarbon reacting with air. The products are always carbon dioxide and water vapor in an open system. Exothermic reactions are going to be labeled as, let's ignore that video for a sec. Exothermic reactions are going to be labeled as a negative energy value, usually measured in kilojoules, because again, the system is releasing or losing energy. Remember, we are talking about the stored energy. It's losing the stored energy and releasing it to the surrounding environment. So we're going to always put a negative in front of our value anytime you hear the word energy being removed, energy being lost, energy being released, energy being produced, and so on. Those will all be negative. Now here's a combustion reaction for you, showing again that exothermic process. You usually see heat, light, and that again brings up what's happening here. As the system, or the reaction, I guess I could say, is losing energy, and I'll just put delta H to represent energy, the surrounding environment is gaining that energy. And so what's going to happen to the surrounding environment is that its temperature is going to heat up. It's going to feel warm or hot depending on how much energy is released by the reaction. Okay? Another thing to note is that the amount of energy is directly proportional to the amount of substance reacting. And this will make more sense once we start talking about the formula. But the formula is really based on taking the amount of substance reacting into consideration. So if you have twice as much reacting, you're going to have twice as much energy being produced or lost, depending if it's endo or exothermic. Okay, so what we're going to get into now is looking at the three ways of communicating an enthalpy change. We're going to look at the three ways for an exothermic reaction first, and then we'll look at the three ways for an endothermic reaction. So the first way of communicating an enthalpy change is by putting it in what we call delta H notation. Some people might call it delta RH. Remember again that R just means a reaction. So the heat of a reaction can be given as a delta H value on the outside of the equation. If it's an exothermic reaction, that delta H value is going to be negative. So let's say we look at the following example. Sulfur dioxide reacting with oxygen to make sulfur trioxide. At this level, you're not going to need to know how to calculate that just from a chemical reaction. Later, we will learn how to do that. But for now, you're going to be given enough information to be able to write what's happening here. So let's say you're told that this reaction is releasing a certain amount of energy. You are then off to the side, so the reaction is written separately. Off to the side on its own, you're going to say the delta H is whatever the value is given to you. And again, you're going to have a negative there because it's exothermic. Okay, we're looking at exothermic reaction examples right now. So if a reaction is exothermic, where the delta RH is written off to the side, it's a negative value. In this case, this reaction releases I should say, 197.8 kilojoules, and we illustrate it as being a negative value since heat is being lost. Now that's the first way to communicate the enthalpy change of a reaction, writing it separate as delta H notation. Next, we can write it as a term inside the equation, and we already looked at this in the cellular respiration and the combustion reaction. Energy will be included as a product. So when you write the reaction, this is actually all one big combined equation, okay? The sulfur dioxide and oxygen making sulfur trioxide also produces 197.8 kilojoules of energy. Now remember, when you're looking at a reaction, everything on the right are your reactants, and everything on the, everything on the left are the reactants, and everything on the right are your products. Now sometimes students will look at this and say, why did the negative go away and now it looks like there's a positive? One thing to note when you're reading a reaction, that positive isn't telling you whether it's positive or negative, it's an and. It's saying this and that are being formed, okay? So the enthalpy change has not changed to positive. It is in delta H notation a negative, but when we write it as a term in the equation, we're not putting whether it's positive or negative. We're just saying that it is being produced as an exothermic process. So it is a product, okay? And I'm sure you can kind of guess if it was endothermic, well, that must mean energy is a reactant, which is true, okay? So just for now, looking at this exothermic reaction, that is how we show energy as a term inside the equation. The last thing we can do is draw a potential energy diagram. Now, if I were to do a quick sketch of a potential energy diagram, it's going to show the relative potential energies, usually measured in kilojoules, as a reaction proceeds. So on the bottom, you might see something written like reaction progress, okay? When I have an exothermic reaction, my system is losing energy. So that means my reactants are going to start at a higher point, and the reaction energy is going to go down to making my products, okay? So notice again, this is a downward trend taking place. So what's happening is the system is losing energy. The energy is decreasing. If we were to look specifically at the example that we just did, where we had sulfur dioxide reacting with oxygen, and it was producing sulfur trioxide, whenever you draw a potential energy diagram, you could put the specific reactants and products in there. It is decreasing, okay? And this height here is your delta H, okay? The delta H was negative 197.8 kilojoules. Now you don't have to draw this whole little squiggly line, and it doesn't matter where you write the delta H, just understanding that this is going down and that's the value it's going down by. So you might be using or hearing words that the products have less stored energy than the reactants because energy has been lost to the surroundings. Okay, so the potential energy diagram for an exothermic reaction, again, your reactants versus your products. The products are lower than the reactants. The stored energy has been lost to the surrounding environment. Okay, now let's look at those three ways for an endothermic reaction. So delta H notation, again, this shows the enthalpy off to the side of the equation on its own. It's not part of the equation. So this is my same reaction, notice, but it's the reverse process, the sulfur trioxide decomposing rather than being formed. When you flip a reaction, that flips the enthalpy change. So when the enthalpy change in the formation of sulfur trioxide was a negative exothermic value, the decomposition will be that same value but now positive. That's going to come up important later on in the unit. So the delta H, written again off to the side on its own, is now a positive value because this is representing an endothermic reaction. So if you're told the system is gaining or the system is increasing by a certain amount of energy, you know it's endothermic, and therefore the delta H notation has a positive for the energy value. If you were to put that as a term in the equation, it now becomes a reactant. So this is all written in one equation. And again, we can separate my reactants from my products. On the, let me check my hands to make sure I know my lefts and rights. I have to check for the L. On the left is the reactants, and on the right is the products. Okay? So energy is now included as a term in the reactant side because the reaction is absorbing or gaining or reacting with that amount of energy to make the reaction take place. Okay? And then, as a potential energy diagram, let me draw a quick reference for you. This time, my system is gaining potential energy. So my reactants are going to start lower down, and the reaction as it gains energy is now going to store that energy in the bonds of the products. So my enthalpy change is going up. My products are going to have more stored potential energy than my reactants. So remember again to always label when you draw a diagram or a graph to label your axes, your X and Y. Now let's look at this specific example for that reaction. So when sulfur trioxide decomposes, and notice that this is not a simple decomposition reaction, just like the formation was not a simple formation, because it's not the elements making the compound, or it's not breaking into the individual elements. It's breaking into a smaller compound and an element. So it wouldn't be classified as a technical, simple decomposition reaction. Now, my delta H for this reaction, and again, sometimes I forget to put the R. It depends on your teacher how picky they are. I'm not usually too picky about it, but you'll definitely see it written with letters, so it's always helpful to remember what that means. It's positive this time, 197.8 kilojoules, because what's happened in this reaction, the products have more stored energy than the reactants because energy has been gained by the system, okay? So potential energy of products is higher than reactants for an endothermic reaction. So I believe we have a sample diploma question, and then the lesson is over. Which of the following statements is true for an endothermic reaction? I'm hoping when you guys write tests and quizzes in your diploma, you're using something to highlight or underline to make sure you're reading questions very carefully and taking your time. Now, if it asks you for delta EP, that's just like the potential energy diagram. Delta EP is the same as saying delta H. It means the same thing. So go through each of these. You could pause the video and see if you can get the answer. But I'm going to explain the process, the thought process you want to go through to figure this out. I would go through each and see if they're correct or not. So is the potential energy or is the delta H for the reaction negative for an endothermic reaction? It is not. It should be positive. The delta H is positive for endothermic. Is for B energy a product? No. In an endothermic reaction, the energy is a reactant. For C, does the temperature of the surroundings increase? Remember we said when I have an endothermic reaction, the reaction is gaining energy, the surrounding is losing energy. So the temperature, of the surroundings is supposed to decrease or feel cool. So hopefully the last one's correct, process of elimination. But if it's asking you about the potential energy of products versus reactants, draw a quick potential energy diagram. And we know that when we have an endothermic reaction, the potential energy increases. So that means that yes, the product potential energy is higher than the reactants. Okay, so D is the correct answer. And that, I believe, is it for this lesson. Thank you very much for watching.